Okay, all right, we're good to go. So, let me get a sheet of paper and just write some stuff. The final is 30% of your total grade. Homework is 10, heavily graded. Most likely what will happen is that the individual with the highest score homework-wise gets bumped up to a 12, and then that shift is given to everybody else. So everybody's going to get pretty darn high homework scores. If you don't turn in homework, that's the thing that kills you. There have been quite a few C minuses that I gave out only because when I looked at their homework scores and it said they submitted 2 of the homeworks. I understand everybody misses 1 or 2. That's expected. You missed 8 out of 9. I'm not looking at anybody in particular, just general. I just enjoy seeing your look. But if you missed that, had you done the homework, you would have gotten better test scores and homework scores to go along with it. So test 1, 15, test 2, 20, test 3, 25, final 30. The tests are out of 100 points. The final is out of 200. So if you get 100 on the final, that's a 50%. Tests, normally I plan on 1 hour, 15-minute tests. Because that's the typical time length that we have for class. And they have 25 multiple choice, 1 appetizer problem, and 3 regular problems. 1 appetizer is 5, 3 problems is 45. So that's where we get the 100. 2 points each for the multiple choice. For the final, you are given a maximum of 3 hours. One of the things that you guys need to be aware of is I am not worried, but you need to be made aware of you could have been spoiled taking tests 1, 2, and 3 because you have 2 hours and the test is only geared for 1 hour 15. This is going to be a legitimate 3-hour final, as in I plan on the max being 3. For the tests during the summer, I don't plan on a max of 2. I just plan on hour 15, and I know that we can't do anything afterwards, so I might as well give you the time. For the final, 50 multiple choice for a total of 100. There will be 2 appetizers for a total of 10 and 6 problems for a total of 90. And so that's 200 points. Effectively, what I'm doing is I'm taking a test, doubling its size, and there we go. During a normal semester, it is a little bit of a luxury on the final because they go from 1 hour 15 to 3, double the length, but then they get more than double the time. For summer classes, it's double the length, but only an increase in 50% of the time. So you guys need to just be careful about that. Really what I am doing, as I have said, I am similar to you guys. Some call it laziness. I disagree. I call it efficiency. What I'm going to do is, for the multiple choice, each of those test 1 multiple choice banks have about 50 to 75 questions. And what I'm going to do is I'm going to give each of those multiple choice banks 1/3 of the multiple choice set, so that it's kind of evenly distributed, and then I still randomize it, but I'll try to keep it even in terms of 1/3 from test 1, 1/3 from test 2, and 1/3 from test 3. I don't know. It really depends on when I look at the multiple choice. Will there be figures? I don't know. but you can at least see what the potential figures are. There'll be nothing that you've never seen before. As for the problems, and once again, there was that tweet to me the night before the third test, and it said, do you have any suggestions about what's going to be on the test? And I said, Dr. Eschenberg, his review sessions are the tests. Like he's thinking it through. And when you look at those, the 3 problems, I did that spring oscillation problem during lecture. I did the Atwood string problem in lecture, added the twist of the lambda. Had to make it a little bit of a challenge, but it's not much. The Bernoulli's equation, I did that. And then the Doppler shift problem, did that. So if you paid attention to that review session yesterday or 2 days ago, you would have been fully prepared. The final is a little bit more unusual in the sense that I do have 6 problems to ask. And granted, I have 2 appetizers. And in a perfect world, there's going to be 2 problems from each of the tests. But it doesn't always work out that way. Metaphysical certain problems. Vector addition. Can you add 2 vectors? One will be an instant conversion vector. The other one will be a non-instant conversion vector. Add the 2, give me the resultant, give me the equilibrant. There we go. All Eschenberg students have to know about vector addition. And it's something that I see as I don't consider it important, I consider it bedrock. If you don't understand how to add a vector, you're no good to me in terms of 213 and 214. Everything is about vectors. Rotation where alpha is equal to 0. We did rotation where alpha isn't equal to 0. I've been thinking about this. Well, let me just let it unfold. Similar to, it's basically in the Fisher-Fury class of problems. So vector addition is test 1 material, rotation is test 2. There will be some sort of buoyancy problem for test 3. And so that's going to be part of it. Also, Atwood's machine, most likely motion rather than energy. And then there's a reason why that I'm gonna do it that way. Atwood's machine motion is test 1 material. The thing that I'm looking at, the reason why I'm going to do motion for the Atwood's machine is that I need to reserve the energy equations for another problem, for a problem that wasn't asked in test 2. So this is going to be a test 2 material problem. It's going to have collisions, which is conservation of momentum, and an energy problem to go inside. So it's kind of a hybrid problem. The big one that I think is, I've used it before, we're going to do it, let me see, are we going to do it? Yeah, on in the spring 16 final, it was done, and we're going to talk about that. So that leaves me with the That last problem, I'm not so sure yet. So this, that, and this, I've been thinking about. You could have pipes, half or whole. We're going to cover one of them today. Oh, duh, then I definitely know what's going to happen. The third, problem 6, it is test 1 material, which means these are probably going to be both test 3, is 2D motion. With a final, granted, I have 6 problems to play with. That's a lot of problems to deal with. However, the material is just so vast. So I have to hit the high notes. I have to hit the big guys. Vector addition, rotation, buoyancy, Atwood's machine, collisions and energy, 2D motion. That's enough. Which means that these, those can be like pipes, oscillations, we do things with like, I mean, it may end up being that one of the appetizers is going to have you read the number of nodes and antinodes, stuff like that. Fall 16's appetizer were oscillation and sound. Oh, yeah, and here's another thing that could be. If I have the time, torque bar. So they'll either both be test 3 material, or one will be test 3 and the other one will be a torque bar.
And that's between both appetizers?
Yes. Yeah, so I would say one will definitely be test 3 material. That's a fact. I need to look at that torque bar problem, and I'll either, and that means I really have to water it down just a touch, and make it simple. But the torque bar may be the other problem. So it depends on.
What do you mean by nodes?
Like, how many nodes are in that one? How many antinodes in the third harmonic? And just stuff like that. So that's what I'm leaning towards. I mean, there's some things that I just go do. I can't give a final without 2D motion, or vector addition, or buoyancy, or Atwood's machine, or collisions. I mean, those have to be in there. Yes?
Repeat what you said about the vector addition. You said it's going to be one with what and the other.
One is, and in fact, that's a good question. It will be a lot like, probably for the vector addition, if we have time today, I'll do them. But we've done enough vector addition where I think it's, yeah. But the vector addition, probably in my case, I would say do give the equilibrium. But the 270 vector, that's instant conversion. That's negative 6y hat. Boom, done. The 4 meters at 110, you got to go through the steps of find your reference, break it into components, and then move on. So with the vectors problem, it's going to be a lot like that. So there we go. So are there any? You may. All right. So here's stuff to bring. The regular green Scantron. There was one year where I actually asked, I had a multiple choice section that was actually 55 multiple choice questions long, which means I had to flip the green sheet in the Scantron reader. That's too much time for me, so we're sticking with 50 max. That's all we got. You can bring your usual pens, pencils. erasers, all sorts of stuff. Markers, highlighters. You could bring whatever your favorite calculator is, hopefully unprogrammed. Really hopefully programmed. Put cell phone in bag. And you can leave it at the front of the room. If I find a cell phone on you, that's points. Bad, bad, bad. I will have my cell phone on in the event of a tornado attack. So, in that unlikely possibility. If you want to, you can bring a ruler. Couple of my recommendations for a happy grader is a generous grader, and graders appreciate great penmanship, and just write it clearly. I will bring probably 2 reams of paper into the room for the final. So if you want 1 problem per page, remember that when you use your paper, don't write in the upper left-hand corner, because when you staple it, you're going to cover that area, which means that the grader has to pry your final apart, which makes the grader upset, which then leads on to point decay and destruction and tears and ashes and disappointment. If you do bring drinks, just as before, you can bring snacks or whatever. Don't be loud. And clean up after yourself. Any drinks, I'll say it again, if you bring soft drinks in here, technically I'm not supposed to allow it, but if you do, that's okay. Just remember to take it outside and put it in the garbage can in the hallway, not in here, because we'll get an ant trail. And because of the rain, the ants are currently inside the building waiting for sugar to hit the floor. And so if that happens, then they'll come out and wreck the place. What I would do in terms of review material are all of the test and final reviews for this semester. The stuff that I've posted. And also, not necessarily the, like during the spring semester and other places, we would do night test reviews. And those are fine to take a look at, but specifically, I would take a look at the 2 lectures preceding each of the tests. And then I would go and look at this lecture here. That should give you enough. If you can go through all that stuff backwards and forwards, you're good. Problem sets. And I know it's difficult, and a lot of you, you still have a lot of stuff outside my office. We will keep that stuff outside my office probably until the Wednesday after the 4th of July, because that's when the next homework set is due for 214. And when that happens, we're tossing everything out with the exception of the final. So tests, homework, it's all gone. But look at the tutorials, because what I'm doing is I'm working through all the problems over and over again. You should be fine. On Blackboard, the multiple choice solution sets have been posted where I've highlighted all the answers. So you can go through that and take a look. And then I would really go through all the tests, multiple choice that you've done this semester. Because really all I'm doing is granted, a few of them weren't asked in some of the tests, but they're all just gonna get mixed up into a big pile and then given to you. So a lot of them you'll go, did that, did that, did that. It'll be fine. And that's really, granted, we only got a weekend to get ready for this, but if you go through those 3 things and can work them backwards and forwards, you're ready for the final. In terms of the final, if you do 80% on the Scantron and then just get half credit on all the problems, you passed. I mean, you're just in. I mean, so it's, and you can just trip over, you can trip over a C pretty easily. So I need you guys to not be panicked. I need you guys to go in, be calm, and then we'll get this done. So anything about the questions about the test in terms of the layout, procedure? Yes.
Are you gonna have one of those quadratics on there?
I promise that there will not be a quadratic on the test. Yes, thank you. One of the things that I will do, I did it before test 3 because my paranoia is growing more and more, is 2-3 hours prior to the test. Normally I walk in and I do the test with you guys. Now I'm going to do the test before and see if there are any corrections that need to be made. I will say that I apologize for that quadratic to be in the test. I understand that it went against my philosophy, but I didn't see that problem existing until 15 minutes before the test, and I didn't know how to handle it. That's why I went to the board and gave you one of the answers and basically set it up for you so that it really wasn't that, I didn't think it was that big of a deal. If it was during a regular semester where I had only an hour and 15 minutes rather than the full 2 hours, because I know it takes a little bit more time, then I would be way more panic stricken and go, oh, I need to fix this right now, and then make a quick change. But I got burned, I understand, but the best lesson's the burned hand. And so that's something that over the weekend I'm going to pay attention to. Like with that Bernoulli's equation, there was no freaking way that it was going to be a negative pressure. I was not going to allow it. And there was no way that the velocity of the fluid coming out of the pipe was going to be 2/3 the speed of light, like I did that first year. You learn from your mistakes. All right, anything else before we crank it up? All right. What I'm going to do is I will skip the vector additions. If you want, what I'll do is I'll post the vector addition answers on Blackboard so that you can use them and work with them as examples. Oh, okay. I misread the problem question totally. All right, this is going to be the fall of 16 test or final. A simple pendulum of 2 meters has a 20 kilogram mass at the end. Let's remember, there are 3 types of numbers on physics tests. 1, numbers that I give you because you need them. 2, numbers that I don't give you because you don't need them. And 3, numbers that I give you that you don't need. Which is the irrelevant number in that first sentence? The mass. 20 kilograms is irrelevant. It's mass independent. A valid question to ask is, and I looked at it and I was like, what? T in this case stands for what? Period. For a second there, I thought it was tension. I was like, you're telling me I got to figure out the tension of the string in a simple pendulum? We've never done that before. So that's a valid question to ask. So what I did is I needed T of Earth over T of Moon. T of Earth is 2 pi L over G. And that's G of the Earth. T of the moon, 2 pi L over G prime. The lengths are the same, 2 pi's are the same, so all these cancel. We all know about how much Dr. Eschenberg loves stuff to cancel. Anything that he can cancel, he won't have to plug into his calculator. So that leaves G prime over G square root. G prime is 10 over 6. G is 10. 10s cancel, and we're left with whatever the square root of 1/6 is. And that's it. That's appetizer 1. Now we have appetizer 2. Now the appetizers are really quick. They're you could sit there and get them done in a minute or two. Appetizer 2, we have a half pipe. Once again, the velocity of sound will be given as 350. What is the fundamental frequency, first overtone, and second overtone for the following half pipe? Pipe only being half a meter long. What I'm really looking for are the frequencies of 1, 3, and 5. First and second overtones are third harmonic and fifth harmonic. They skip the evens. So F1 is NV over 4L. N is 1, V is 350. The pipe is 1/2. So we're left with 175, no, not you. Did I get it right? I don't know. I'm too tired to care. 350 divided by 2. I was right. 175. And so that is the first harmonic. Now you need to find the third harmonic. So all you do is you multiply 175 by 3. 525. And then for F of 5. Oops, that's not what I want. Okay, so those are the answers. I heard someone say, where did what come from?
Where did the 2 and the 4 come from?
Where does the 2 and the 4 come from?
Oh, 2. I think you did 2, 2, 4.
So that's the 4. L is 1/2 because I said 0.5. So what I did is I canceled or multiplied 4 by 1/2 immediately to get the 2. Okay. Vector addition will skip. I'll post answers. 2D motion. 2D motion is we have, it'll be one of two things. If it's like this, I have to give you time. And we may, let me see what the other 2D motion was. No, the other one was still not level. If it's an uneven surface, I have to give you time. Otherwise, we end up with quadratics, and we all know how much we love those. I'm looking for V0 and theta. You do the classic, find the origin. You set up as positive and right is positive. It's a 2D motion problem, so you're going to write x equals x0 plus V0 xt, and y equals y0 plus V0 yt plus 1/2 at squared. The V0, there is no ax because it's 0. You plug in your zeros. X naught and Y naught. Oh no, no, what did I do wrong? Y naught is non-zero, Y final is 0. Because the Y final is there, Y initial or Y naught is up here. So the Y initial is going to be 200. Anything in green we do know. I know time. I know X. V naught X is V naught cosine theta. And we don't know any of those. So this is a 1 equation, 2 unknowns. So we can't deal with that just yet. 0 equals Y naught plus V naught sine theta t plus 1/2 AT squared. I know t. I know I'm on the planet Earth. A in this case is -10. I'm looking for V naught and theta, and Y naught is given. This is a 2 equation, 2 unknown problem. So what we're going to have to do is we're going to have to substitute one of the variables out. Typically, because theta is sitting inside a cosine function, and we're not really big on understanding the intricacies of what goes on in a cosine function other than the ratio, we'll solve for V naught. And we get that. Plug that into here. T's cancel. What did I forget? There's one itty bitty thing that I forgot to go from here to here. The sign. When I substituted V naught became X over T cosine theta. There it is. The T comes down, but the sine theta didn't. And I'm left with Y naught tan theta X plus 1/2 AT squared. I'm looking for theta. So minus 1/2 AT squared minus Y naught equals X tan theta, or minus 1/2 AT squared minus Y naught over X is tan theta. So theta is inverse tan of minus 1/2 AT squared minus Y naught over X. So that gives us minus 1/2 -10 10 squared minus 200 over 100. Negative 1/2 times -10 is 5. 5 times 100 is 500. 500 minus 200 is 300. 300 divided by 100 is 3. So this is the inverse tan of 3. 71 point. I'd accept 71.6, but I need the extra digit for accuracy. So 71.56. Plug that in here. V naught equals X 100 T 10 cosine 71.56. 100 divided by 10 is 10, so this is 10 divided by cosine 71.56. 31.6 meters per second. And so that is it. Just the classic set up your origin, identify your zeros, identify what you know and don't know. One will either be a one equation, one unknown. If it is, attack that first. If it's a two equation, two unknown, solve for one of the variables and just treat it like a normal two equation, two unknown problem. Number 3. Given the conditions shown, what is the final velocity of the system the moment before impact? In this particular situation, I'm asking only for the final velocity. Which technique is the quickest way to find final velocity? Energy. You attack this with energy. Now, most likely the one that you get on the final will be motion, but it's always good to do this. The equation that you start off with is energy initial minus the energy removed through friction is the energy final. The way that you look at this is that in the initial conditions, it is not moving. It has just overcome static friction. So the initial energy is potential energy, and it is M2GL. The final energy is the collective kinetic energy of the system, which is 1/2 M1 plus M2 V squared. The V is what we're going to look for. Now, we do our usual sum of the vertical forces on the mass is 0 for mass 1, which means that this is M1G or minus M1G plus normal force. So normal force is equal to M1G. Friction force is mu sub K Fn, which is mu sub K M1G. Now, the work, force times distance, is mu sub K M1G, the friction force, times L, the length. So this gives you minus mu sub K M1GL. Solve for V. First step, factor out GL for just cleaning up the thing a little bit. Solve for V squared. Square root it. And that is V. Where did I what?
Well, you made it over to the left a little bit.
Oh. If you need to sneeze, it's funny, it just reminds me, if you need to sneeze during the final, just let it out. There was a student who tried to not sneeze during a final, and it sounded like an exploding elephant calf. It just was like, and it was far worse. It was far worse than the sneeze ever could be, which made it hilarious. It was awesome. So this becomes 2 times 10 times 12. Oh, and I was a jerk. Okay, hold on. There's one last thing that I need to do. I will most likely put in a substitution not a trick, but you got to use the substitution technique. In this particular problem, M2 is 3 times M1. So you can't get V for the moment. But what you can do is that. Factor out an M1 out of there and add those together. And you're left with 2GL M1 3 minus mu sub K 4 M1. And I get this. So it is 10 times 12 3 minus 0.5 all over 2. Now this is probably the fun part. 10 divided by 2 is 5. 5 times 12 is 60. 3 minus 0.5 is 2.5. Let's see, did I figure it out? Times 2.5. So that's the square root of 150. And that apparently was the closest I was going to get. So it is 12.25 meters per second. It's actually 12.247. So that is problem 3. Oh, I love 6. God, I love 6. I may just copy and paste 6. That is a good idea. Well, since I talked about it, let's hold it off until last. Number 4, playground physics. Now, technically, it's not an alpha equals 0. Number 4 is a, it's an alpha equals 0 at the beginning and an alpha equals 0 at the end, but you have the conservation of angular momentum in the middle. This is the same problem that I talked about before, where you've got the 3 kids at the edge of the merry-go-round. They move towards the center and it effectively whips the 4th kid off the wheel, much to the amusement of everyone except the poor kid. All this is understanding moment of inertia before and after. The moment of inertia before is the moment of inertia of the disk plus 4 times the moment of inertia of those children. The moment of inertia afterwards is still the moment of inertia of the disk plus 4 times the new moment of inertia of the children. Initially, they were all at 6 meters. When you look at the picture, the new R is 1/3 of the old R, which means that the new R is 2. So this becomes 1/2 mass of the disk, R squared, plus 4 mass of the child, R squared. And let's just get a number for this. 1/2, 150, R is 6, mass of the child is 30, 6 squared. And I'm left with 7,020 kilograms meters squared. The new moment of inertia is 1/2 mdr squared plus 4 mass of the child, new radius squared. That leaves you with 1/2, 150, 6, 4, 30, 2. And so you get that. So I could see this, the rotational one where alpha equals 0, being either a conservation of angular momentum or a Fisher-Fury style of problem. All I want is the new frequency. That's all I need. So this is conservation of angular momentum, L initial, L final, and they're equal to each other. This means I omega I prime omega final. You have to understand that 2 pi f is equal to omega. So this becomes I 2 pi f equals I prime 2 pi f final. That's the new frequency. The 2 pi's cancel, which means that IF divided by I prime is your final frequency, which is the answer. The old I, 720 or 7020, the new I, 3180. The old frequency is 2. So the new frequency is 4.42 hertz. And that is the playground physics problem. Number 5 is a problem that I made all by myself many years ago. Probably it was the first year that I taught 213. And it was one of the first initial problems that caused me great frustration because students couldn't figure something out. So Molly decides to take a slide down an inclined plane as shown on the sketch. So it is 1/4 kilometer down. There is an angle of 20 degrees. There is no friction. Yay, no friction. Now what's really funny about this problem is that at the time, Lafayette High School physics class would come and visit every semester just so that he shows the students, look, this is the stuff you're going to do. And I would do the Molly Dolly problem. Years later, one of the students comes into my class and takes my course and tells me that his teacher was the one who made the Molly Dolly problem. Because they're 2 pandas. And I was like, well, what are the names of the pandas? And he says Molly and Dolly. And I was like, that's because that thief stole my problem. Stole the names too. So it's flattering, but I made this one up. So Dolly down here is at rest. Molly is at the top of the hill, initially starts at rest. We have no friction. Yay, no friction. So we don't have to worry about that nonsense. Molly comes down the slide and it was really weird. I'd stayed up late that night and I'd written this whole backstory on Molly and Dolly and why had they seen each other in a while, why would they hug, and blah, blah, blah. And then I was like, just give it up and say they just hug, and that's it. So Molly and Dolly are twins. They're identical twins. They are identical twins. So if Molly's mass is 75 kilograms, what's Dolly's mass? 75. Next question. Why could my class not get it through their thick skulls that Molly and Dolly had the same mass? One of them said, well, what if one had a sandwich? And I'm like, they didn't have a sandwich. They didn't have a glass of water. They're identical twin pandas. And so they're both 75 kilograms. Thank you. So Molly comes down, and what we have to do is we have to figure out the energy of Molly at the beginning and at the end. It's entirely conserved because there is no friction. So the potential energy initially is the same as the kinetic energy at the final. This is pre-collision. The potential energy is mass of Dolly, GH. The kinetic energy at the end is 1/2 mass of Dolly, V squared. The masses cancel. And I'm left with 2GH is equal to V squared, or V is the square root of 2GH. The only question that we have is we don't know the height. But we do know the angle and we do know the hypotenuse. We can get the height from that. That makes it sine of theta is height divided by that length. So height is L sine theta. So this becomes square root of 2GL sine theta. Which means that the velocity of Molly at the bottom of the hill is 41.4 meters per second. The next thing we have to do is we have to calculate an inelastic collision problem with Dolly because they stick together and hug. I need to know the velocity of the twins immediately after the collision and what is the ratio of energy after collision divided by energy before. So really what we're looking for is the ratio of the energy remaining. It's an inelastic collision problem. So momentum initial is momentum final. Momentum initial is mass of Molly times her velocity equals the combined mass of Molly and Dolly with the final velocity. Now, Molly and Dolly have the same mass. So those cancel. And the final velocity is that initial velocity of Molly divided by 2. And so that is 20.5. Oh, I can't divide. 20.7 meters per second. That's the velocity of Molly and Dolly after impact. The last bit, hold on. No, I came up with a problem. I don't know if it's going to work. Now, velocity final is 20.7. I'm looking for the energy after over energy before. So the energy before is 1/2 mass of Dolly, velocity at the bottom of the hill squared, divided by 1/2 Molly, or actually I'm getting all these turned around. That's Molly, plus mass of Dolly, times their final velocity squared. those two masses is 2m. That is 1m. So what's left is VB squared over 2 V final squared. So this becomes and so we get that. This is what did I do wrong and how do I fix it? The question is, I want the ratio energy after divided by the energy before. Is that the energy after and is that the energy before? No. So all I have to do really is just flip it. So that should be on top and that should be on bottom. And really what I get is you flip that, you flip that, you flip this, and I get 2VF squared over VB squared. Now, what's the best way to figure out, had I used this, would that number be greater than or less than 0? Or I'm sorry, greater than or less than 1, as written here. That number would be greater than 1, because I would have the energy before divided by the energy after. And since the energy after decreases due to the collision, I would get a number greater than 1, and then I would be very confused. This, on the other hand, will give me a number less than 1, which is exactly what I should get. And I get 0.5. Had I used this initial equation, I would have gotten a number of 2, which means that the energy after the collision increased, which is inconceivable, or it's just impossible. Now, number 6, I was quite proud of coming up with number 6. Number 6 is, it does look very familiar to a statics problem that we did for problem set 7, I think, 7 or 8. But it's underwater, and the object is less dense than water, so there's going to be a buoyant force up. So the first thing we really need to do is just look at this object and get the forces all straightened out. T2 is to the right. T1 is down. You have the buoyant force up, which is the density of the fluid water, because it's always going to be in water unless I say otherwise. Volume, gravity, and then you're going to have the mass of the object times gravity down. And so those are the forces. Now everything needs to work in a vertical and a horizontal manner. So T1 needs to get divided into T1x and T1y. Now one could ask the following: what is it doing? Answer: nothing. And if it's doing nothing, it's obviously doing something in terms of its translational sums are all equal to 0. So we put the parts in together. Sum of the forces in Y. Buoyant force minus mg minus T1y is equal to 0. Sum of the forces in X. T2 minus T1x. And so those are the sum of the forces in X. There's only 2 in the horizontal, but 3 in the vertical. Now, the way that this thing is drawn, that angle is 30, which means that angle is 30, which means that sine of theta is T1y over T1, and cosine theta is T1x over T1. So we get that. Substitute it in. 0 equals rho of water, V, G. Now we don't have the mass of the object, but we do have the density. Get the Swiss Army knife equation ready to go. Density is mass over volume. Therefore, mass is density times volume. So mass is the density of whatever material that is, I'll just use rho, times the velocity times gravity minus T1 cosine theta. T1y is T1 cosine theta. Now the whole point of this is to find T1. T1 cosine theta is GV rho W minus rho. Yes?
Is T1 not sine? Or is it
T1y is, yes, thank you. And you get that. So T1 is GV rho W minus rho. And that's over sine of theta. So now I have GV rho W, rho, and theta. So that gives me 10, 5, 1,000 minus 500 over sine of 30, which I love to use because it is actually 1/2. So 50 divided by 1/2 is 100. 100 times 500 is 50,000. 100, oh, yeah. Yeah. So it's 50,000 newtons in tension 1. The other equation, which we couldn't have solved because we didn't know anything about T2 or T1 at the time, T1x is equal to T2. T1x is T1 cosine theta. So this is equal to 50,000 cosine 30. And that gives me 43,301 newtons. And so that is the hybrid. It combined a little bit of vectors and forces with buoyancy. Okay, all right, good. So that is fall 16 final. What I'm going to do now is anything we'll skip certain things. One, for spring 16 final, we'll skip number 3. I'll put the answers out. Appetizer 1 we did on test 3. So I think you guys did fine on it, so we're not going to have it. And I got buoyancy problems that I need to put in there anyway. Appetizer 2 is a valid problem to put on the final as an appetizer. It's a simple torque bar problem. I'm not looking for that force, I'm only looking for tension. So to do that, I have to say that the sum of the torques is equal to 0. My 3 torques are, well, let me label this. Dude didn't label this at all. I'll just say R1, R2, and R3. R3 is 3, R2 is 2, R1 is 1. The 3 torques, and we're going to choose the pivot point as the fulcrum, is M1GR1, M2GR2, and then TR3. And currently my brain is having a war about, I mean, there's no reason why I couldn't put that Harrier jet problem as the appetizer, but I've decided against it. It's going to be a conventional one like this. We got to get our torques signs straight. M1 is to the left, down, up is positive. M2 is to the right, down, in, or negative. T is to the right, up, out, positive. So we get this. All I'm looking for is T. M2GR2 minus M1GR1 equals TR3. So M2GR2 minus M1GR1 divided by R3 is T. M2, 5. R2, 2 minus M1, 1. 10, 1, 3. So this is 5 times 10 times 2 is 100, minus 10 is 90, divided by 3 is 30. Exactly. Wow, I put in a lot of energy problems into this guy. Problem 1. Problem 1 is a lot like, we're going to skip it just so that we can save the time for other things. This is, the setup is like, this is why we're not going to do it. Setup is exactly like this. You do a substitution, you set up with energy, that's fine. It's not a motion one, so I'm not gonna deal with it. What we could do, I'm gonna change it. Instead of asking for the final velocity, I want to know what is the acceleration and the length of time for this thing to reach the bottom. You may only use equations of motion, no equations of energy in this problem. So to do this, we're going to have to use our loopy-droopy number line and set up our forces. So we've got this. We've got mg down, tension right, normal force up, friction force to the left. to get the normal force, we have to sum the vertical forces first. That is Fn minus m1g. Normal force is equal to m1g. So friction force is mu sub k m1g, because friction force is mu sub k Fn. We sum the forces in the horizontal on this guy. Sum of the forces in x, which is equal to m1a, is equal to t minus mu sub k m1g. And we get this. Solve for tension. m1a plus mu sub k m1g is equal to tension. So that's the first one. In the sum of the second masses, we have tension up, we have m2g down. In our loopy-droopy number line, up is negative and down is positive because left is negative and right is positive. So the sum of the forces vertical is m2a, which is equal to m2g minus t. So t is m2g minus m2a. T is equal to t. The strings have the same tension. So m1a plus mu sub k m1g is equal to m2g minus m2a. Solve for a. m1a, m2a, I get this. A I get this. And I get that. So I'm looking for A. 10. Ooh, we got to do one last thing. Do a substitution. M1 is 1/5 of M2, or M2 is 5M1. So 5M1 minus mu sub k M1. M1 plus 5M1. This gives me G M1 5 minus mu sub k over 6M1. This gives me 10, 5 minus 0.1 divided by 6. I also like the substitution because it just eliminates stuff before I calculate. 4.9 times 10 is 49. 49 divided by 6, 8.17 meters per second squared. In the way that I set it up, is the negative answer possible? No. This thing's definitely going to go to the right. The coordinate system has right as positive, so it's got to be positive. What's the maximum value for this thing? 10. So if you get an answer that's greater than 10, which some of you did, or you get a negative answer, which some of you did in test 1, you got something wrong. So you got to go back and double check. The time that it takes for it to fall, that's a one-dimensional motion problem. Origin, that is 20. You're given A, it starts from rest. So x equals x naught 0, v naught t 0, 1/2 at squared. So 2x over a is t squared. So t is the square root of 2x over a. .21 seconds. So that's an Atwood's machine done with motion. So something like that will be on the test. Be able to get to that equation, and then you can solve for everything. There will be friction. You may even have to solve for friction, I don't know. But something like that will be on the test. Number 2, problem 2. Problem 2 is the conservation of energy and momentum lab. The one thing that wasn't given here, that it was written on a sheet of paper, but I didn't put it on the test, is that angle is 30 degrees. What we're doing is we're working backwards. The question is, I need to find the initial velocity of that mass. First, we have to do the conservation of energy. Then we'll do conservation of momentum. The conservation of the energy part occurs entirely after the collision. So it's unnecessary to worry about an inelastic collision because it hasn't happened yet. It starts here, combined mass, at a height h, which means the potential energy there is m1 plus m2 gh. Now its angle is 30 degrees. Its final energy is all in kinetic at that, well, there's no friction, yay, no friction. 1/2 m1 plus m2 v squared. Now that's post-collision. Post-collision velocity, I'll give a letter, let's just say P, as in post-collision. Those energies are the same. And I get this. Those cancel. The one whoopsie thing that I haven't figured out yet is what is the value of h. And so for h, you're going to have to use a little bit of trig. The length of the arm is L. So if it rises to a height L and that L is saying, it rises to a height h, that is L, that's L, so this length here is L minus h. And we get that. To extract h out of this, I need to know that cosine of theta is adjacent L minus h over L. So L cosine theta is L minus h. Or h is L minus L cosine theta. Or L 1 minus cosine theta. So 2g L 1 minus cosine theta is equal to the post-collision velocity squared. I substituted that into this to give me this. Square root it. V post is the square root of 2gl 1 minus cosine theta. And I get that. So the velocity, the post velocity is 2 times 10 times 0.4, 1 minus cosine of 30. So 1.035. That's the post-collision velocity. That's the velocity that it had at the bottom before it rose to the top and came to a stop. The last bit of this is a conservation of momentum problem. We're studying the inelastic collision. Momentum initial before the collision is momentum final. The initial momentum is m1v1. The final momentum is m1 plus m2 post-collision velocity of vp. Vp is the final velocity. You look confused in the back. Are you okay? Okay, good. No one look at her. She's very self-conscious in the back. Okay. So we're looking for this guy right here. V1, M1 plus M2, M1 VP.
Okay, I'm gonna stop. She was looking because I'm confused. All right, listen.
Now, here's the thing. If you're confused, raise your hand because I'm sure there's somebody else who does this. Now, okay, I believe that you speak for the class. So let's hear your confusion.
I don't know how you got the height. I thought that's what the cosine said, right?
So let me, okay, what in the experiment, let's just take a look at the graphic. What do you do in lab? You fire that ball out of the cannon. The ball hits the arm. They merge together, and then it raises a particular distance. That angle is the angle that you measure in lab. That's a height h. So you have the potential, at this particular point, you can figure out the potential energy of that h. That h you can't measure directly. You know the length, well you could if you pulled out your little calculator or a ruler. But you know this length here, that arm length does not change. So if that is length L and that is length H, that is length what?
You asking me? Why?
If
all right, that is length L and that's length H and that's length.
all right, let me draw a bigger picture. So it starts here and ends there, which means that is angle theta. So we know that. I'm looking for this height h. That length is L. It's the same arm, so that length is L. If you draw a dotted line over, if that length is h, then that length there must be of length what? If that total length is L and that length is h, then that length must be what? L minus h. So I have theta and I have L, which means I know that cosine of theta is L minus H over L. It's just the ratio. Solve for H. H becomes this. Now really what we're doing is, in the lab, you fire the ball, there's a collision, it goes up to a height theta. The goal is you need to find the velocity at the beginning of the experiment. So what do you have to do? You have to start at the end of the experiment with theta and L and work backwards. That's the procedure. So what we did first was we found the velocity post-collision. The velocity post-collision is basically a conservation of mechanical energy, or just energy problem. The potential energy at the end has to be the kinetic energy at the beginning. So kinetic energy is this, potential energy is that. We set them equal to each other. We cancel and solve for velocity post-collision. The only thing that gums it up is we have that H right there. That's why we had to go through all of that. Solve for that H. Put that in, and then we get that value right there. So is your confusion, is the back row less confused?
Yeah.
Is all of the back row less confused? You could say something out loud. I won't have them turn around and look at you. Okay, you're good? All right, excellent. To get the last part, M1 is 1, M2 is 5, M1 is 1, velocity is 1.035. Just multiply that by 6. 6.21 meters per second. And so that's the answer for that. It's a really good, both the Molly Dolly one and this one are really good in terms of collisions and energy and stuff like that. And fun fact, that had the Molly Dolly problem had another problem where their younger brother named Tiny was used, and his mass was 4 times that of Molly and Dolly. I know, it's a pun. Get it? He's much bigger, but he's called Tiny. It made me laugh at 3 a.m. So, problem 3 is a vector addition, so we'll skip that. I'll post the answers. So we're down to the last 3. Just so we know, I am the unofficial academic advisor to right field at Swayze. I am personal friends with the right field hater and other right field hate celebrities. In this, J.P. Woodman hits a home run. It flies for a particular amount of time and it lands. This is similar to the 2D motion problem that we did at the in the first test, except now we're dealing with baseball. It's a 2-dimensional motion problem, so you immediately get x equals x naught plus v naught xt, and y equals y naught plus v naught y t plus 1/2 a t squared. Now, y and y naught are both known, so they're not 0. X naught is 0, so that is that. V naught x is v naught cosine theta t. Y equals y naught plus v naught sine theta t plus 1/2 a t squared. In this particular case, the only unknowns that we have are t and v naught. or I'm sorry, take it back, theta and V naught. T is a known quantity. A is known. Y and Y naught are known. X is known. T is known. So the two unknowns in this is theta and V naught. So we go right through the same thing all over again. Solve for V naught. X over T cosine theta is V naught. Y equals Y naught plus X over T cosine theta, I won't forget the sine theta this time, times time, plus 1/2 AT squared. T's cancel, sine over cosine becomes tan, so Y equals Y naught plus X tan theta plus 1/2 AT squared. Solve for theta. Y minus Y naught minus 1/2 AT squared is equal to X tan theta. 1 over X, Y minus Y naught minus 1/2 AT squared is equal to tan theta. So theta is inverse tan 1 over X, Y minus Y naught minus 1/2 AT squared. Close parentheses, and we're good to go. Now plug and chug. You may now plug and chug. 1 over 120. Y final is 3. Y naught is 1. A is -10. T is 7. So that leaves us with 2 plus 5 times 49. Divide by 120. Inverse tan. 64.1 degrees. The last bit, X 120, T7 cosine of 64.1 will give me the velocity that I'm looking for. And I get 39.24 meters per second. And so that is problem 4. Problem 5 is your lab experiment from yesterday. You have a tuning fork of 280 hertz. The velocity of sound in air is 350. You are allowed to lower the level anywhere from 0 to 100 centimeters. There will be more than one answer. So you let the water fall. We've got the tuning fork held over it. It will resonate at particular distances. Typically, I think this thing is set up with 2. What are those distances? It is a half pipe. The water is closed at one of the, or water closes one of the ends. So you have frequency is equal to NV over 4L. What you're looking for are those L's. L is NV over 4F. The harmonics go first, third, and fifth if we even need it. What we're going to do is we're going to find L1. 1 times 350 divided by 4 times 280. And so the first length where it resonates is 0.3125 meters. For L3, it's just 3 times L1. So 3 times 0.3125 that gives us 0.9375 meters. There's no point in using the 5 value because it will give us a number greater than 1. The tube is 1 meter long, so that resonance cannot happen. So it's only those 2 lengths. Problem 6, rebel rod and reel. And while I'm thinking about it, I really don't see me using parallel axis theorem in the making of these moments of inertia. I think it's just going to be straightforward center rotation discs, sticks, and points around the thing. The rebel rod and reel has 120 meters of fishing line on the spool. So that X is going to be 120.
So, like that circle, what was that, test 2? You're not going to do that one? Is that it?
Oh, you mean, well, that one didn't, I don't think it used parallel axis theorem, but it was where alpha wasn't equal to 0. And when I'm looking, and one of the things that I kind of did today is I kind of did a test run on the final that I'm going to do on Monday. And no, I can't see alpha being non-zero on the final. I could see alpha being 0 either A, a problem that we're doing right now, or B, conservation of angular momentum. One of those 2. It will not be, it's not going to be a problem like that, like we got on test 2. There's just too little space. I mean, if I keep asking Vitter for those 8-hour finals, but he keeps saying I only have 3. So you call them finals, I call them celebrations. I would love to spend all day just doing physics. But I know, right? So we don't do that. So I would say by the looks of things, that alpha equaling non-zero can't be, I may talk about it in the multiple choice. That's I mean, anything that I can't do problems of and I still think they're really good, I'll stick them in the multiple choice. Which means they really have to be dumbed down. Because they're multiple choice, they're not a problem. So that answers it. You let 12 meters of line out, so X naught is 12. The fish of fury takes the bait and begins to move away at 12 meters per second. The speed is constant, so V is equal to 12. A lot of 12s in this problem. How long will it take before the spool runs out of line? It's the classic one-dimensional motion problem. X equals X naught plus V naught T. X is 120, X naught is 12, V naught or V is 12, solve for T. X minus X naught, V naught T. X minus X naught over V naught is equal to T. X equals 120, X naught is 12, V naught is 12, so my time 108 divided by 12 is 9 seconds. That's how long it takes. The radius of the spool is 4 centimeters. So that's information that we need. How many revolutions did the spool make when it runs out of line? So the amount of the number of rotations is the length of line in the spool when the bait was caught. So 108. To figure this out, if you've got 108 meters of line and each circumference is 1 meter, let's just say for argument purposes, you would just take the 108, divide it by the circumference, and then you would get the number of revolutions. So 2 pi r, or 2 pi 0.04. $429.72 revolutions. And so that's number 2. Number 3, I'm looking for period, frequency, angular acceleration of the spool while it's in motion. Alpha is equal to 0. This is a Fisher-Fury problem. Alpha is equal to 0. The explanation is V is constant. So V is equal to omega r, and dV dt is d omega dt r. We're doing just a touch of calculus. This means that dV dt is equal to alpha r. If dV dt is constant, or I'm sorry, if V is constant, the change in velocity is 0, which means that alpha is equal to 0. Done. Now for the period and the frequency, if it made 429.72 revolutions in 9 seconds, the frequency is the number of rotations over the total time, 429.72 over the total time, which is 9. Which gives me a frequency of 47.7 hertz. The period is inverse frequency, which gives me 21 milliseconds. So I'll ask for the final units of what I want, but 0.021 seconds or 21 milliseconds would be fine. And so that's the final. We did 2 finals. It's not going to be that bad. Review this lecture, review all the other review lectures. You may want to even look back at a final review for 213 from either the spring or last fall. All of that's online. And good luck. See you next noon on Monday.